Yes, well, I'll go ahead and start introducing you since we're about a minute away. Thanks to everybody for coming. I think we'll probably have a few more people joining here in the next few minutes, but Austin Brunig is going to give us his capstone presentation today. And Austin, just to remind you, you have 15 minutes to present, and then there will be 5 minutes for questions. If people ask questions in the chat, if you could just repeat the question for the recording before you answer it, that would be great. And whenever you're ready, go ahead.
Cool, thank you. Okay, cool. So thanks for joining me today, everyone. My capstone thesis was on shadow reclassification and aerial imagery by correlating spectral compositions. So the problem that I attempted to address is when classifying land cover in any sort of imagery, it's very difficult to classify what's truly underneath shadows, and especially in an urban context, shadows are very prevalent in the imagery. And so my solution is sort of based on this theory, which is that spectral compositions of land cover remain constant regardless of the intensity of that reflectance. So for example, if you have a fully illuminated tree versus a tree that has a shadow casted over it, it's going to have the same band-to-band relationships that you would see normally for a tree. It's just that the reflectance intensity is much lower. So the idea is to figure out a way to associate the spectral compositions that are within that shadowed area to what we know and to a fully illuminated land cover type. And so the method that I chose to use was a statistical correlation test, the Pearson's R, which represents a linear association between two variables, which means that if you have a positive coefficient that indicates a positive correlation, which means that as one variable increases, so does the other. If you have a negative coefficient, that indicates a negative correlation, and as one variable increases, the other decreases. And if the coefficient is at or near 0, then there's no linear relationship between those two variables. So I conducted this correlation test using Python, specifically the pandas data science package, using one of the correlation functions within that package. And this diagram kind of explains how that actually works in Python. So for example, if we have a tree data frame, which would be sort of our known spectral values, and we're comparing it row-wise to our unknown, which is our shadow data frame. So object 0 from the tree data frame is matched with object 0 from the shadow data frame. And the key here is that the schema of each data frame needs to be identical so that you're matching the red band to the red band, the green band to the green band, and so forth. And so what you get is a coefficient that's generated based on that. And my idea is that if you can select the coefficients that are above a very high positive coefficient, then you can reclassify the shadows as such. And I will be using, or I used object-based imagery analysis to segment and classify the imagery that I used. And if you don't know, objects are essentially a collection of spectrally homogeneous pixels. And so you can associate those objects with characteristics of land cover that we know, and that includes shadows. Once you've identified those land cover types, then you can take the spectral composition of each object and then begin the correlation test. So my study area was Boulder, Colorado. I used NAPE multispectral imagery of 1 meter spatial resolution, and it was acquired in 2015. Here's an example of on the left is the full NAPE tile and some color infrared on the right. I also used LiDAR. This was to create a normalized digital surface model, which would help in both the correlation test, but also the initial classification and tagging height attribution to all objects. This was also acquired in 2015, and it's at 1 meter spatial resolution. So the technology that I use, eCognition for the OBIA process, that includes the initial classification, ArcGIS Pro for all the pre-processing, accuracy assessments, and the final maps. And then I use Jupyter Notebook for the actual code development and then running the correlation tests. So the methodology can be separated into 4 big components: the DSM creation, the initial classification, ground truthing the shadows, and then running the correlation tests. So first off, building that normalized DSM, that came from raw LiDAR, and I created 2 different models, a digital terrain model and a digital surface model. And these are the LiDAR classifications for each model. So just ground classification for the DTM, for the DSM, unassigned ground and building classification. I included unassigned because all vegetation was encapsulated in this group. So without having to reclassify, I just included the unassigned classification. Okay, now so going into the land cover classes that I chose to encapsulate the NAPE imagery. So I used 7 different classes: bare grass, healthy grass, trees, pavement, buildings, water, and of course shadows. I also had an 8th class, bare earth, or like exposed dirt. However, the performance of that class was really poor during the initial classification. And so I ended up actually dropping that class and merging those objects with pavement. And the reason why I did that is because bare earth and pavement have very, very similar spectral characteristics, which is why it was really hard to differentiate it. So to kind of normalize it and clean up the data, I dropped it and just kept it with these 7 classes. So the first step in the OBI process is to segment the imagery. And so I used 2 different algorithms in eCognition, quad tree and the multi-resolution. As you can see, I have various weights for the multi-resolution. I weighted the near infrared band really high, and I'll go into why that is. These are the spectral metrics that I chose to use for the initial classification as well as the correlation test. And the reason being is that these bands or these indices are really indicative of differentiating between vegetation and impervious surfaces, which is like the real key when you're looking at urban land cover, is understanding like the differences between that. So you can kind of read through and see, but it's essentially kind of a relationship between the near infrared and the red, and how the dynamics between those 2 bands play into identifying vegetation versus a building and so forth. So this is the final conditional rule set that I use in eCog to classify the imagery. If you look down at the bottom, you see that water was manually classified. The reason I did that is there was such a small amount of water in the imagery that it was just easier for me to go in there and reclassify those objects instead of trying to come up with an algorithm. After each class was classified, everything that was remained, I reclassified those as shadows. Excuse me. So now that I've classified the imagery, the next step is to assess the accuracy of that classification. So I went in and selected 250 sample points for each land cover class directly from the imagery. I did a spatial join to join those points to my land cover map. And then I assessed the equivalency and said, if the sample point land cover is the same as the classified object, then it was correctly classified. So here's the assessment results. So each class did really well, except for that bare earth class, 37%, which is the reason why I dropped it. So the next step, or before we go on that, here's an example of what that land cover initial classification looks like. We got structures in pink, pavement gray, dark green is trees, light green is grass, and bare earth is that yellow. And then shadows are in black. So side-by-side comparison, it did pretty well. So next step is to resegment those shadow objects that I just classified. And the reason I did that is because each shadow object represents the larger extent of a shadow. So for example, if you have a shadow from a tree casting over a sidewalk, but it's also casting over some grass, you wouldn't capture that spectral difference in the initial classification. So the idea is to resegment those objects at a finer scale to sort of try to pick up some of those spectral differences. So you can see that I use the same algorithms, they're just at a smaller scale. So here's an example. The black is the initial shadow objects, and then the resegmented objects are in blue. So you can see how everything kind of got subdivided. Okay, so now the next process is to ground truth those shadows. So I took the 250 shadow sample points for the initial classification, did a spatial join with the resegmented shadow objects. So I have 250 shadow objects. And then I went out using ArcGIS collector to physically ground truth each of those objects. And so here's kind of the land cover breakdown. So the vast majority of those shadow objects were pavement, which makes sense because it's an urban area. But so this is the data frame that I will be using in the correlation tests, because now what I have is the land truth, but then I have all the spectral metrics that I'll try to correlate and see what happens with the performance of that. So the next step is actually to conduct the correlation test. This is an overview of sort of what's going on behind the scenes. So for example, if I have a land cover data frame here on the left, essentially what I'm doing is I'm trying to aggregate each spectral metric and get a random value within one standard deviation of the mean. So I get a random value that's within a range, and I use that representative data frame to test against the shadow objects. You run the correlation tests, you generate a coefficient, and the coefficients that are above a threshold, and for this case, I used a threshold of 0.85, which is a fairly high positive correlation coefficient. Those shadow objects would eventually be reclassified. But the important thing here is that this occurred 100 times for each land cover. So after each iteration, the representative land cover data frame, those spectral values would change. And the idea behind that is that it would try to identify which shadow objects consistently had a coefficient that was above that threshold. Here's kind of a better diagram of how that randomization of those metrics happen. So I got my land cover class here on the left. I got the mean, the deviation, and then I created a high end and a low end. And then using a random number generator, I created a random number within that range for each spectral metric. And that's the data frame that I would use to test against the shadow object data frame. So this is kind of hard to see, but on the left-hand side, after the correlation tests, you have 100 iterations for each land cover. All those selections for each shadow object would get collected into a list. And so the idea now is to count how many land covers occurred for each shadow object and then choose the one that happened most often. So we have a flattening of the data frame, and then we have a grouping and counting for each land cover or for each shadow object. And then it's just a process of finding which land cover occurred most often. So I separated it between two data frames, a selected and tie data frame. And on the left here, these shadow objects have a clear definitive winner. And that land cover was recorded here in this field, and that would be the land cover that would be reclassifying it as. If there was no definitive winner, then it would get put into this tie data frame, and this tie data frame would recycle through that process all over again. However, I capped it at 5 cycles, which means that if still there was shadow objects that still didn't have a definitive winner, then I just marked those shadow objects as unclassified. Okay, so here's the results of the test. I didn't get the results that I was really hoping for, but again, this is kind of the breakdown. So remember, the pavement was the vast majority of the land truth underneath each shadow, and that scored about 88%, which is pretty good. However, healthy grass and buildings did not do well at all. And there's a couple potential reasons why that may be. But overall, I saw 82% correctly reclassified. Okay, so now that I did my sample set, I tested the correlation test. I implemented the correlation test for the entire Nate tile, which remember includes all of the resegmented shadow objects, which equates to about 920 hectares. And here's the breakdown of the results. So this is the land cover area in hectares. The vast majority was bare grass and pavement. And you can see here on the right, there was a fair amount that was unclassified at the end of the test, 39 hectares, which means that there was 881 hectares that were classified, and we could infer that 82% of those were correctly classified, which leaves us to 722 hectares that were properly recovered from this process. Here are the results. I outlined the shadow objects in black just so you can kind of see them. And here's kind of a comparison with the imagery. So, you know, if we look at like this street area, you could probably deduce that pavement is underneath those shadows. And that's kind of what we're seeing here from the reclassification, which is good. Now, of course, you can kind of make out some mistakes, some misclassifications. Here's another example. This is CU Boulder. All right, so like I said, there's potential improvements to improving that accuracy. One of them being using higher spatial and or radiometric resolution for the imagery. So if you're able to pull out more spectral diversity from the imagery, and if your classification is good, then essentially you would be capturing more pure objects, spectrally pure objects. I also thought that potentially proving out this methodology in a less spectrally diverse environment, such as an urban environment, might have been better, just to be a little bit easier to see definitively that this test is actually working. Number 3 through 5 kind of are experimentations that you could play around with to see what works and what doesn't. But looking at different spectral metrics, different coefficient thresholds, and obviously looking at different correlation methods. The Pearson's just one of many. But I think the last one would probably have improved the results the most, and that's removing any outliers from the land cover class data frame before using them in the correlation test. So essentially, I didn't normalize the land cover class data frames. I just pulled them directly from that initial classification. And I guarantee you that there could have been some objects that had some extreme spectral values that when you pull that, when you pull it into the correlation test, that's just going to disassociate the shadow objects even more. So there it is there. Thank you for joining me today, and I'll open it up to any questions. Thank you.
Thanks, Austin. Does anybody have any questions? And feel free to turn on your mic if you want to ask a question instead of typing it.
I have a question for Austin. A great presentation, Austin. You've done a wonderful job, and shadows are the bane of high spatial resolution remote sensing. So let's say here you had 8-bit data. Let's say you have UAS imagery where you have 16-bit data, and such that the numbers range from 1 to 70, 80,000. Do you think that your methodology can be modified to accommodate that?
Yeah, I think the biggest thing is if you're using that higher radiometric imagery, you have like the land cover spectral characteristics have to be pure. And the only way to achieve that is to have a high performing classification. And if you don't have that, then it doesn't really matter what you put into the correlation test. You're not going to get good results. I will say that the higher the radiometric resolution, the harder it is to classify that imagery because you have so much more variance to have to deal with. So that it is a balance between like, okay, NAPE imagery is not that high spatial resolution, there's much higher, but does it make sense to aggregate these spectral compositions to make it easier essentially to classify? So I think there's kind of a balance for both sides.
Okay, and just a quick follow on the computational requirements. So you obviously capped your project to the extent that the computation load was reasonable. Can that get out of hand very quickly?
I actually don't know. I thought that I wouldn't be able to extract the what was it, the over 2 million shadow objects within one shapefile, but it was fine. It came out to like maybe a gig. So I don't really see it as being a huge problem unless you start going into higher spatial or higher radiometric imagery for sure.
Okay, thanks. Great job.
Thanks, JB. So Fritz left a question. He says, this seems like a very practical process. I may be misunderstanding your processes, but I was curious whether you consider looking at the Pearson's R value for individual bands rather than in-band combinations. Would there be an advantage to this approach? Yeah, that's a good question. I kind of thought that maybe that's how the correlation function in pandas worked, but it is a combination of all of those data values. So you're not getting a coefficient for the red band value, you're not getting a coefficient for the green, blue, and then attempting to find the relationships there. I don't know, like I guess that would involve a lot more Python, but no, I didn't go down that route, and I'm not sure if that would be an advantage or not. Beth asks, will you continue to experiment with this? Are you done worrying about shadows? The answer is yes, I'm going to continue tinkering around with it. This idea was completely original, and it was really supported and fostered by JB, and so there's a lot of creativity that was involved and a lot of passion that was involved with it, and I think that because of that, yeah, I'm really psyched to just like keep diving in and seeing if I can improve it, because I think in the end it could definitely help. Yeah.
That's great. I think the creativity and passion are obvious. So fantastic job. Oh, it looks like you have one more question.
Okay. So Matthew asks, did your study consider using alternate approaches such as cross-validation to improve your model's accuracy? Which is, so do you mean like using another land cover map to validate the performance?
Hey, Austin. Yeah, so
Hey.
This just happens to be like leave P out cross validation, leave one out, K full cross validation. It's just other machine learning approaches.
Mhm.
And I don't know if you went that far, but I was just curious.
Yeah, no, I didn't go that far. I think like my machine learning knowledge is very limited, even though I think this has principles of machine learning. But yeah, I didn't look at that. I think that's kind of the gap is like I was trying to figure out what can be possible with just ground truth objects and knowing what's there and then extrapolating that to the larger nape tile. So I'd be curious to look at different approaches or different QC standpoints. So
Thank you. That's all I needed to know. Thanks.
Great. Well, again, great job, Austin. Thanks for taking the time to present today. And I am recording, so if you want me to, I'll give you the link to that in case you want it. And thanks to everybody for joining in today. We will be meeting again tomorrow at 11:50 for 3 more presentations. So have a good day, everybody.
thanks, Beth. Thanks, everyone.